All right, in this video, we are going to introduce Cauchy's integral formula. The first one, there are two of them, so we abbreviate this one CIF1. Just a brief recap. So far, as far as the integral theorems are concerned, we have seen Cauchy's integral theorem, which says if a function f is analytic in some region R, then the integral of f of f along a simple closed contour in that region is going to be equal to 0. So what this is saying is, suppose this is a domain or region where f is 0, where f is analytic. So if we integrate f of z along any closed contour, then it's always going to be equal to 0. So this could be our closed contour, or that could be our closed contour. So of course the closed contour could take any shape, so long as it is inside this region where f is analytic. Then the integral around that closed contour is going to be equal to 0. Of course, this follows from what we saw earlier. We demonstrated via examples that if you have got any 2 points and your function is analytic, then the integral from one point to the other is exactly the same along one path as the integral along another path. So if you call this one C1 and call this one C2, then the integral of f along C1 and C2 will be exactly the same. Now, what this means, of course, is that if we integrate from this point to this end and then integrate along the other contour, then the two of them are going to cancel out because they're equal. But now this one is reversed, and so that is the consequence of that is Cauchy's integral theorem. Now, so Cauchy's integral theorem, so therefore Cauchy's integral theorem deals with the case where the function is analytic. So that means the function has got no singularities inside or on the simple closed contour. So Cauchy's integral theorem deals with the case where f of z, or the integrand, is analytic. If it's analytic, it means it has no singularities inside, our closed contour C. So that means as soon as we have a case where there is a singularity inside, then so if f is singular at this point, then the Cauchy's integral theorem is not going to enable us to evaluate an integral along or around this contour C. so we are going to be stuck. Well, in fact, this leads us to it necessitates the Cauchy's integral formula. So Cauchy's integral formula deals exactly with the case where now there is a point inside our contour C where the integrand is singular. So let's look at the statement of this Cauchy's integral theorem. So it says let f of z be an analytic function inside and on C, and z naught be any point inside C. So far it looks like there is no singularity happening. Okay, then it says the integral of f of z over z minus z naught, okay, is going to be equal to this term here where C is traversed in a positive sense. So now the fact that we are dividing here by z minus z naught, it means this integrand here is going to be singular at z naught. So that's how it caters for the case where we've got a singularity inside. So this is going to be our contour C, and this is going to be a singularity. Now again, because of the deformation or the independence of path principle, the contour C could be any shape. It could be a rectangle like that, so long as the singularity is inside. It could be a circle, it could be an ellipse, it could be anything, any contour that is going to enclose that singularity or that point z naught is going to work for this result here. So let's look at a proof for this theorem, or well, formula, because the theorem is already taken by the first result that Cauchy discovered. So since the function f of z over z minus z naught is analytic everywhere inside and on C except at z naught, okay, because when you plug in z naught, they're going dividing by 0, the principle of independence of path applies. So the principle of independence of path is related to another principle called the principle of deformation of path. The fact that we got independence of path, it means you can deform your contour and still have the same integral. So that's exactly what I was talking about here. If you start with this contour here, you could deform it into a circle or deform it into a rectangle or square, so long as it still satisfies the same properties, that is, in this case, it encloses that singularity. Okay, so what we're going to do is we are going to consider the integral along a circle around the singular point, z naught. So we are going to say consider, so for the left hand side we got integral of f of z over z minus z naught dz along C. This must be equal to, say, another contour which we're going to name gamma. Now this contour is going to be a circle dz. So where gamma is a circle of radius r, and it's going to be centered at z naught. centered at Z0. So what are we saying here? We're saying, okay, imagine we started with this as our C. We are going to deform this C into a circular contour. So we're not going to have a circle around Z0, and the radius of this circle is going to be equal to R. Okay, so that means the circle is going to be defined by the equation mod Z minus Z0 is equal to R. So we can do this. We can deform this path C into this path gamma. Since they both enclose Z0, then the integral around C of this function must be same as the integral around gamma. Now, so if gamma, along gamma, we have mod Z minus Z0 is equals to R. If we write this in parametric form, it becomes Z minus Z0 equals to R e to the I theta. Of course, R is a constant. From here, Z is going to be Z0 plus R e to the I theta, and dz is going to be RIE to the I theta d theta. So we can now rewrite this integral here in terms of the parametric equation. Okay, so thus the integral around gamma of f of z minus z minus z0 dz is going to be equal to the integral of f of, z is z0 plus re to the I theta from here, dz is RIE to the I theta d theta, and then the denominator z minus z0 is just RE to the I theta, and then now the variable is theta, so we're just going to be integrating from 0 to 2 pi, or we can say from minus pi to pi if we like. Now some of these terms are going to cancel out straight away, so RE to the I theta is going to cancel out. Okay, so this thing is going to be equal to I integral from 0 to pi of f of z0 plus RE to the I theta d theta. Okay, however, by the principle of deformation of path, the integral of or this integral must be the same around this circle of radius r. However, we could make r smaller. It should still be the same. Or even smaller, it should still be the same. Smaller, even, it should still be the same. So long as our contour or our circle is still enclosing Z0, then this should still be fine. Okay, so we can actually let r take the limit as r goes to 0. The two integrals, this integral and this integral, should still be the same. Okay, so that's exactly what we're going to do. So since f of z over z minus z naught is analytic and hence independent of path, independent. In fact, in this case, we don't need the over z minus z naught, because what we have now here is just f. Okay, so since that is independent of path, we can take the limit, or let's just say the value of the integral should remain invariant, okay, it shouldn't be function of the size of the circle, should remain invariant in the limit r goes to 0. Okay, so that left hand side should be the same as this integral in the limit r goes to 0, f of z naught plus r e to the I theta d theta. However, so we take the limit as r goes to 0, this term is going to disappear. So this thing is just going to be the integral from 0 to 2 pi of f of z naught d theta. However, since this now does not depend on theta, we can factor it outside the integration. So it's just going to be the integral of d theta. So there's going to be f of z naught times I into theta evaluated between 0 and 2 pi. And when we do the substitution, this is going to give us 2 pi I times f of z naught, which gives us the right hand side of the formula. Okay, so that just gives us a feel or the derivation of Cauchys integral theorem 1. So we are now going to look at some examples of how to use this formula in the next video.